Hey, welcome to the next Gen I with Sai YouTube channel. So as of now, we have completed three lecture sessions. The first lecture session was about a basic NLP basic. Second is about text pre-processing. Third was about feature engineering in NLP. And now we are going to work on we are going to have the fourth session, which is bit advanced in the NLP. So let me explain what we are going to learn today. First, we will cover, these are the outline by the way. We will cover text similarity, uh, how we can check whether the two text similar or not. Then we will touch upon the NLP model building, um, and then how once the model is built, how we can evaluate that model. Once the model evaluation done, how we can do the validation and the testing. Okay. After that, we will touch upon the Zipfs law, uh, and then we will learn how we can capture the context of the word, then word embedding, and these are the two things, that is word to vec. Okay, just one thing, these are not the in-depth lecture because these are just a touch upon the all concepts. Okay, definitely I'll create another video series where we will go in depth. Okay, but the purpose of this lecture or purpose of uh, this is the NLP for everyone, right? So when I say everyone, so don't just say that it's a data scientist. Data scientist, non-data scientist, anyone. Okay, so we will just touch upon purpose is just everyone should aware about the concepts. Okay, at least the terminology. For in-depth things, we will create the different lecture for that. Okay, so I hope you understood what is the outline of today's lecture. Let's move to the first point, that is the text similarity. Okay, now how we can do the text similarity? Let me write down the headline here, the text similarity. So first of all, what is text similarity? Let's say there are two sentences. The first sentence, um, again, I'm playing, right? And the second sentence, maybe I'm watching. I'm taking very simple example, right? Let's say these are the two sentences. So I want to see how these two sentences are similar to each other. Now, to check these sentences are similar, there is a one trigonometric function that we are going to use called as a cos. Okay, and as we are using this trigonometric function to check the similarity, it is called as a cosine similarity. It is called as a cosine similarity. Okay, now there is a formula to check the cosine similarity. What is the formula? The formula is this: cos theta is equal to product of two vector. This is called as, by the way, this called dot product. This is called dot product. Okay, to check the dot product divided by norm of two vector. So we have two vectors, right? A and B. So sorry. Okay, so norm of A into norm of B. Okay, so this is called as a norm of, or yeah, this is called as the norm. Okay, normalized vector of this two product A and B. So this is the mathematics. Now whenever answer of these two vector, we are getting in the range between +1 to, sorry, -1 to +1. The result always coming between the -1 to +1. So whenever the output is close to +1, then we are saying these two sentence, okay, or whatever the sentence we have, that two sentence is similar. Sentence similar, I mean to say the meaning of these two sentences are similar. Whenever there is a -1 means they are dissimilar. Okay, so always remember the range of this is coming between -1 to +1. Okay, now remember, as I earlier in the last lecture in the feature engineering, I told you this A and B is nothing but the vector representation, is nothing but the vector representation of your sentence, or I can say word. Okay, now in the geometry, whenever we draw the x-axis and the y-axis, okay, let's say this is the two vector A and B, means the vector representation of A and B. Now to convert this vector representation A and B, we are using different method. Okay, yes, in last lecture we have seen some of them. Just if you don't know, so let me tell you. For example, we can use TF-IDF or word to vec. Most popular is a word to vec, where we are converting the word into the vectorized format, right? And there are many more. Okay, so using these technologies or using this concept, we are converting word to vector format. Now once it is converted into the vector format, we will apply the cos. We will apply the trigonometric function cos theta. Now if this cos theta, as we can see, the theta between A and B is very close, so these are sentence, I can say, close to similar, right? They are similar. So now you understood. To check the text similarity, I write down the sentence here. To check text similarity, we are using cosine similarity function. Cosine similarity function. Okay, now don't worry, in my other lecture, other video session, I will show you on the notebook how we can, using the Python, we can calculate the cosine similarity. Okay, but I hope you understand the theoretical part behind it. Okay, fine, great. Now let's jump to the next topic, that is called as a NLP, model building and evaluation. NLP, model building and evaluation. NLP, model building and evaluation. Now in NLP, model building and evaluation, before that we are doing some kind of process, right? So what are the general steps we are following while doing the model building? The first step is data collection and pre-processing. Data collection and pre-processing. So this is the first step in the data in the NLP model building. Now this pre-processing, if you miss my previous lecture, previous session, then please watch out that the second session where I deeply explain what is the pre-processing. But in general, it is something nothing but the we are doing some tokenization, in removing the noise, do the inconsistency, apply stemming, lemmatization. So let me note down for just if you. So first is the tokenization, right? Then do some kind of removing noise. Then we are doing, apply some stemming and or lemmatization or combination of both. So these are the some of the techniques we are applied during the pre-processing, but there are many more. Please watch out that video for detailed understanding. Now once we apply this data collection and pre-processing, Then we will go for the second step called as the model selection. Model selection. If it is a classification based model, like if your objective is a classification, right? Let's say if it is a classification, right? Then for example, spam detection or the sentiment analysis. Okay, for that we are using the some kind of ML model like navy bias, svm, support vector machine, decision tree, etc. Okay, this kind of model we are using. If it is a sequence type of model, right, it is a sequence type of model, for example, rnn or lstm or the grus, right? If these are the kind of network we are using for the, okay, so all these are the, by the way, neural network model. Okay, deep learning type of model. Okay, so these models very helpful where sequence is associated. For example, if I give the example, translation, right, where sequence is very important. So in this case, this sequence model we are using. Now there are the advanced model we can nowadays everyone is using, that is called as a transformer based model. Okay, for example, BERT, GPT, okay, GPT-4, 3, etc. All these are transformer model. These transformer model is called as the powerful model, powerful or state of the art model in NLP. Okay, and they are giving very good accurate result, and they are very enough to scalable. So once we selected the model based on our problem statement, then we go for the model training. This is the model training. Now in the model training, what we are doing, we use the data, we use the data, right? Which data? It's a pre-processed data, by the way, remember. We use this pre-processed data, then the model. Now when we are feeding this data to the model, we need to do some adjustment. Okay, along with the some internal parameter we need to tweak, right? Now after this, once we feed it, we need to do some kind of hyperparameter tuning. Hyperparameter tuning. Okay, so what is hyperparameter tuning? Hyperparameter tuning is something that control the model control model learning process. Okay, model learning process. Okay, why this parameter is needs to be tuned? To achieve optimal performance. To achieve optimal performance, right? For example, if I want to give hyperparameter, the number of activation function or the number of hidden layer, these are the hyperpar, or the number of epoch. Okay, so in maybe in advanced course when I'm going to explain you, that time you will understand what is hyperparameter tuning. But just for a sake of understanding, you can say to achieve the optimal performance or to achieve the good result, we are doing this kind of hyperparameter tuning. Okay, then yeah, so this way I think these are the some of the steps we are doing for the model building. Okay, so let me just revise once again what are the steps we are following in the model building. The first is the data collections and the pre-processing. Once the data is collected, once we apply the pre-processing, then we go for the model selection. Now there are different ML and the deep learning, and the state of the model is there based on our choice, based on the problem statement, and the resources we are available, we are selecting one of the model. After that, we are go for the model training, which is the last step. Okay, in the last step we are feed the data pre-process model to the model that we have selected, do little bit adjustment in the parameter, and do the hyperparameter tuning to achieve the optimal results. Okay, and after that we will get the final model. Now this is the end? No, this is not the end. We have to do some kind of evaluation whether the model is giving the is up to the mark or not. So therefore there is some evaluation method, and for that evaluation method we are using some kind of we are using confusion matrix. Now what is confusion matrix? Maybe in your machine learning you are aware about that, but the confusion matrix is n by n matrix. So it's basically something look like this. Okay, I'm taking very simple, but it is doesn't require that it only 2 by 2. So this is what the actual value of yes or no, or I can say positive or negative, and this line is something the predicted value. These are the predicted value. So it can be again positive and then negative, right? Now let's say my model predicted my actual value is also positive, and my model is also predicted to positive. So this is called as a true positive, right? Similarly, my actual value is negative, right? And my model is also predicted negative, so this is called as a true negative. But let's say my actual value is negative, but my product model predicted positive, then it is called as a false positive. Someone they also say these are the type 1 error. In statistics, this considered as a type 1 error. Type 1 error means the predicted value is type 1 error means predicted value is positive but is false, right? This is called is false, or I can say negative. Okay, this is called as a type 1 error. Okay, the second is the my actual value is positive but predicted as a negative. So predicted is what? Negative. So that's why I'm saying false negative. Okay, so this is called as the type 2 error. This is called as a type 2 error. So what do you mean by type 2 error? Type 2 error means the predicted value is similarly predicted value is negative but actual is positive. Okay, actual is positive. So this is called as a type 2 error. Okay, type 1 is a false positive, type 2 is a false negative. Let me use the different color. Yeah, fine. So we always try to reduce the false positive and the false negative to increase the accuracy, because that is not good for our model, right? So I hope you understood what is true positive, true negative. Okay, so for just for everyone, wherever I'm saying P is nothing but the true positive. It's a true positive. Wherever I'm saying PN means true negative. Wherever I'm saying uh, false FP, it's nothing but the false positive. And wherever I'm saying FN, it's nothing but the false negative. Okay, simple. And the false positive is also called which type of error? Type 1 error. And false negative is also called as a type 2 error. Okay, so this way we can do the model evaluation. Now there are some, based on this there are some metrics. Okay, as of now this is a confusion matrix. Now let's build some metrics. The first metric is called as a accuracy matrix. Okay, now what is accuracy matrix? What is the formula of accuracy matrix? Your total true positive plus true negative, okay, divided by the true positive plus true negative plus false negative plus false positive. So it measures your overall correct prediction. It measures your overall correct prediction. How many values are predicted correctly is nothing but the accuracy. Next is the precision. Okay, next is the precision. Now what do you mean by precision? Precision is nothing but the your true positive divided by false positive plus true positive. Now if you look at this, false positive means we wanted to understand the how many actual positive out of total positive prediction. This is called as a, okay, so the model gives it some prediction, right, the positive prediction, but out of that actual how many are truly positive. Okay, this is nothing but the precision. Next is the recall. Okay, next is the recall. So what do you mean by uh, recall? Recall is nothing but the your true positive, again it's a true positive, but from your actual positive. So false negative and the true positive. So this is the, this is nothing but the positive. Okay, this is nothing but the actual positive. Okay, out of okay, so um I should not be say actual positive, by the way. Here also the true positive. Okay, I can say the true positive out of actual positive. Okay, so what is the difference between the precision and the recall? The difference between the precision and recall, in the precision, it, you can remember this way: P stand for prediction, right? So from actual positive prediction, how many are true positive? And in the recall is nothing but the from your actual positive, how many predicted as a positive. Okay, so this is called as the recall. And then third is the F1 score. Third is the F1 score. So what do you mean by F1 score? F1 score is nothing but the, this is also called as the harmonic mean of precision and recall. What is this called? Okay, let me write down here. This is also called as a harmonic mean of precision and recall. So how we can calculate this? This is a 2 into precision into recall divided by precision plus recall. Okay, so this way you can calculate whenever the precision and importance both are required, both are important, then that time we can use this harmonic mean of precision, right? So as I can say, accuracy is general, it's a general model to calculate the accuracy, right? Precision focuses the positive, on the positive of your model predicts. Okay, so you can say that out of all cases your model classifies as positive, how many were actually correct, right? Right, and the So generally, if you say spam filter, right? If you take the example of let's say your example, a spam filter. Okay, spam filter. So number of correctly identified spam email divided by total number of email the model classify as a spam. Okay, so this is something a spam. Recall focus on completeness of your model. Okay, so we write down this thing also. The precision focuses on the positives of your model, right? And the recall focuses on the completeness of your model. Completeness of your model. Okay, so out of all actual positive cases, how many models correctly identify? So again, if you take the spam filter, number of correctly identify emails divided by total number of actual email, and the F1 score, it combine the both. Okay, it combine the both of your precision as well as recall. Okay, so see why F1 score is required, because when we say high precision, let's say the value of precision is high, it means that model rarely makes the mistake when classifying the review as a positive. And when we say high recall, it means that model identify most of the actual positive review. Okay, so if you combine this, then we will have the advantage of both precision and recall. Okay, fine. So this is the something basic about the, and in maybe in some other lecture I can show you there are some Python library is available to calculate the precision recall. Now the second is the ROC curve. ROC curve. So ROC curve is nothing but the it's a classification model. Okay, uh, so some problem face the issue with the accuracy. Okay, so what is the long form of ROC? ROC is nothing but the receiver operator characteristic. Okay, so it is the curve that has, so if you have false positive rate, okay, so this is a it is a so this is a FPR, that is false positive rate, and the y-axis we have TPR, that is true positive rate. Okay, false positive rate and the true positive rate. One second. We delete this, and this is a FPR, means false positive rate. So it is generally very good for the uh, uh, generally for the classification based model. Okay, so we are second. So when we are drawing, so it will give the curve like this. So this value is ranging from 0 to 1 and 0 to 1 here on y-axis and the x-axis. So if the area, which is this area, so this is sub receive operator characteristic, and this area is called as AUC, that is area under curve. Okay, so if value of this area under curve is equal to 1, it means that the classifier model is able to distinguish between your false positive and the true positive clearly. If it is 0, if value of AOC is equal to 0, then is not able to distinguish clearly. Okay, so so in this AUC and the ROC curve, okay, So area which is under the curve, okay, say as this as a 1, okay. So if area under the curve is 1, then says that the model is able to distinguish between your true positive and the new false true positive and the false positive. Okay, so AUC value generally lies between 0.5 to 1. Okay, so better, which is close to 1 means it's a good classification between your false positive and the negative. Okay, sorry, false positive and the true positive. The second evaluation model that use is called as the, one second, it's called as the BLUE. Okay, so BLUE stands for the bilingual evaluation uh, under study score. Okay, so this is used to evaluate the, generally this is used to quality of machine translation, quality of machine translation. Okay, so how it will check, it will do the comparison between the human generated, uh, human created, not generated, I would say human created translation with the machine generated translation. Okay, so this, it will do comparison between the human created and the machine generated, and based on this comparison it provide the score. So this way this blue score is working. Okay, I'm not going in depth, I'll create the separate video for that, but this is the context about the blue. Now we finish with the model building and the model evaluation things. There are many more, but just I want to give the basic things. Next is the validation and testing set. Validation and testing sets. Now what do you mean by validation? Now generally we know that the data is, it is recommended to divide it into the three sets. Okay. One is the training sets, second is the validation set, and the third is the testing set. Okay. Now this training set, it is used for a training the model. Validation is used for the, this is used for the fine tune the hyperparameter, or I can say hyperparameter tuning. Okay, so it will increase the epoch or number of layers, hidden layer or activation function. Okay, and check whether the model is overfitting or underfitting. Okay, so this validation set is very important to check this kind of thing. And the testing, it is generally for the final evaluation. Okay, so this is, this testing is generally the unseen data. Okay, so when you are doing testing, check for the unseen data. The validation data is mostly from your training data, but testing is something from the unseen to check the generalization of the model. Okay, because we want, our purpose is to have the generalized model, right? That is the purpose. Okay, so it will check the generalization of the model. It should work in all conditions. So this way we have this kind of uh, things. Additional consideration while doing this, to check the model explainability. Okay, so other parameters also we need to consider. It's called as a model explainability. Model explainability means, see how model makes the prediction, how model makes prediction. This is called as a model explainability. Second, we also need to mitigate the bias mitigation. Okay, means we make sure that our model is fair. Okay, it should not bias to any of the thing. For example, if I want to doing some kind of house prediction, okay, so it should not only consider the highly populated area. Okay, it should consider the all kind of area, all kind of other features also. It should not bias to some type of data. Okay, so we have to consider that bias mitigation. Okay, so this is something about the next topic. It's called as the zip law. Okay, zip law. So what is zip law? Zip law is a uh, name after the one of the American linguistic scientists called as the George Kingsley Zip. Okay, so this person is a American linguistic person. Based on this, the law is considered as a zip law. So it observes the frequency distribution of word across the various language. Okay, so what is this law? It states that the frequency of word in a corpus, let me note down, frequency of a word in a corpus. So when I say corpus, the corpus is nothing but the large collection of text. Corpus is nothing but the large collection of text. Okay, is inversely proportional to its rank. Okay, so in simpler term, what I'm trying to say that the most frequent word will appear roughly twice as often as the second most frequent word. Okay, and three times as often as a third most frequent word, and so on. Okay, so those words are we use frequently, it appears roughly. Okay, its rank is very low, so frequency is high, its rank is low. This is called as the Zipf law. Now no need to remember, okay, because this criteria is also useful. Why we are using Zipf law? To do the data analysis. Okay, so we check the how this vocabulary rich. Okay, so to check the richness of vocabulary, we are using this zip law. Similarly, in the information retrieval also, this zip law is used. Okay, information retrieval means for the search space we are using the zip law to improve the search efficiency. Okay, so by prioritizing the term used on their expected frequency, retrieval system can focus on most likely relevant document, right? So this way we can use this zip law. Next is the language modeling. Okay, in the language model we can also use the zip law to predict the next word, to predict the next word. uh, this is also for the thing, but there are few limitations. Okay, I have explained the application, but there are few limitations of zip law. What are those limitations? The first limitation, it is not the perfect fit. It is not a perfect fit for the evaluation. Okay, real world language of usage might deviate from the zip law because there are many factors. What are the factors? The factors are like proper noun, right? Then there are technical jargons, right? Specific writing style. These are the things. Third is the corpus. Okay. So zip law hold for the larger corpus, but for smaller data set, okay, for smaller data, this zip law is not correct. Okay, not giving the things correctly. So I hope you understood what is zip law. Okay, if you want more detailed explanation, let me know. We will have the another things in detail. The next is we are going to see the next topic. This is called as a context of a word. Okay, how I can understand the word context, right? So for that, to understand the word context, we were having the bag of word or the TF base. So this represent the text in the number form, but it only cover when we are using the TF idf or the bag of word. This only cover the syntactical aspect of the word. What it cover? Syntactical aspect of word. But to understand the semantic, this methodology is not helpful. So for that, we are using the word embedding technology. Word embedding things. Why? So that we can have the semantical aspect as well. Semantical aspect of word. Okay. So to achieve the semantical aspect of the word, we are using the word embedding. The most popular word embedding model is, let me, the model is uh, word to vec. Okay, is a word to vec. So what is word to vec? This is one of the second. Yeah, this is a word embedding model. It's a shallow network model. So when I say shallow network model means it has one or only few hidden layers in between. Okay, now you can see if the my neural network only have one or two or few hidden network, then that is called as a shallow neural network. If it is a deep, then I have multiple hidden net layer, then it is called as a deep. Okay, this model is developed by the Thomas Michaud in 2013 at the Google. Now how it is a most popular technique in word embedding, by the way. How it is developed? Now if you look at this example, let's take the example of the this thing. If I have the vector king, okay, if I do the minus of vector man, and if I add the queen, it gives the result of vector woman. Okay, so this is a very one of the popular example of word to vec model. Similarly, uh, so if you do this addition, it will able to predict the vector woman. Okay, now when I'm talking about the, so how it is possible? Because it's able to capture the semantic relation between this. Okay, uh, now if I explain the architecture, there are the two architecture of this thing. One is the, you can have, let's say you have word, you have the sentence. So there are two architecture. The first architecture, you are giving the context word, and based on that it will try to predict the target word. The second architecture says that you are giving the target word and it will predict the context word, and all this word to vec is doing on the unstructured data in unsupervised manner. So word to vec is a actually unsupervised technique. When you pass this, you will get the output into the v cross d. What is v? V is the size of the vocabulary and d is the number of dimension to represent that each vector. Note that this d is a variable in size. It generally depends on the corpus size and the relation between the word that you need to capture. Generally, this d size, that is the matrix size or the number of vector size, varies between the 50 to 300. Now, this word to vec model which Google has developed is trained on the Google News data set. Okay, and that size of that word to vec, it train on the 3 million words. Means you can say the vocabulary size, the value of mod of v is a 3 million, and the dimension of that word to vec model is a 300 dimensions. Okay, so the Python gensim library provide this pre-trained word to vec model, and you can use this pre-trained model for your training. Now if you want to train, how you can train? You use this two methodology. One is a skipgram and another is a cbow. Cbow is a continuous bag of word. Okay, So in CBOW, as I explained earlier, you are going to, let's say you have these words, okay, learn to say before you sing. Okay, so say this is the target that you want to predict. So what you are going to do, you are taking the window size of 5. Window size of 5 means before and after the target you are taking the two words. Okay, now you are passing this word target. This is one training data set. Okay, and your output will be your target. This is the context, this is what you want to predict. So your data set will be like this. Your target, sorry, so let me just erase. So your training data set something like this. This is your target and these are the context one. Okay, context 1, context 2, context 3, context forward. So this way you are passing the data to this type of neural network. So when you are passing one word to your model, it will predict the next four words. So how many words to predict, it depends on the window size. So this is called as a graph. Similarly, the CBOW is the, you're passing the context word. Okay, exactly opposite me, you are passing the other word except the target, and you want to predict the target. So this is something the architecture of the CBOW. Okay, so and it is follow the bag of word things, bag of word concepts while doing the training. So this way you can build the model. Okay, so I hope you understand how the word is converted into the vector using the this technology, the skip gram and the cbow. I know that I haven't explained in depth, but at least you got how the word to vec architecture works and how it is predicting. If you follow this kind of vector operation, you are able to predict what is the next thing. So this way you can develop the semantic meaning of the things. So I hope you understood the NLP session 4. So what we have covered in NLP session 4, we understood these topics. Okay, let me just go. These topics we have covered: text similarity, NLP model building and evaluation matrix, what is the validation and testing set, zip law. These are I haven't covered in depth, but at least give the little bit idea what is zip law. Then how to capture the context of the word. Okay, what is word embedding and how it will help to capture the context of the word. And the last topic I have covered the word to vec, which is one of the important model in the word embedding. I hope you understood. If you have any question, please don't forget to do the in the comment section. Okay, see you soon in the next lecture. Till that time, keep watching.